So after introducing you to it last week, this week's video is going to be much more detail about inverse square law, particularly how you can actually make it work in the real world. We're going to talk you through an example of using it on a large scale, an example of using it on a small scale. One thing I should remind you, of course, is inverse square law is a law of physics. So whether you want to learn about it or not, you're still going to have to deal with it. So it probably helps if you can get your head around it. So again, let's look at that in practice. So here's our starting image, but now let's look at how the shot was lit. Now we can see from this setup shot that the distance from the light to the subject is around a foot, 30 centimeters or so, and then that the distance from the subject to the background is perhaps more like 50 centimeters, 45, so perhaps a foot and a half, and the whole area is fairly small. Now obviously we're exposing for the espresso cup and getting that exposure correct. If we apply inverse square law, or if we think of how it's going to work in the real world, then of course by the time the light gets to the background, its distance has more than doubled. Okay, so it's gone from being correct at 30 centimeters, a foot or so, where the espresso cup is, to being 2.5 feet maybe. So more than doubled from what we've marked as our correct exposure point. Therefore, the light hitting it is only about a quarter or less than the light we're exposing for where the espresso cup is. And therefore what it means in practice is that something that we know to be white, this background paper, in fact turns into a mid, even a dark grey. If we switch to a point where the light is further from the subject and the light itself is also further from the background, so in fact the relative distances between the subject and the light and the subject and the background have now come down quite a lot. Look how much it changes. We've now got a background wall that is much brighter, much closer to the white that it actually is. Because if we look at the measurements, we've got, say, 2.5, 3 feet from the light to the espresso cup, and then maybe a foot and a bit from the espresso cup to the back wall. So if you think back to that chart of distances and the amounts of light, they're now in a much closer ratio to each other. So we are still exposing for the espresso cup. But because the espresso cup and the background wall are now relatively closer together in relation to where the light is, they fall into a similar plane in terms of how much light is falling on them. So the background wall is now much closer to white. If we were, of course, to put them right next to each other, well, they would both be in the same amount of light, the same plane, if you will, so they would be lit exactly the same. Now, of course, that might be exactly what you want. You might want very flat, featureless lighting. But understanding this inverse square law in practice means you can manipulate objects and your background and the subject to hopefully create as much depth as you want in the image.
So let's go ahead and try and look at how inverse square law will actually apply in real-world photographic situations. Now, here is a real-world photographic situation. Look at that. That's very real-world. We have a light here. Obviously, you can tell because, look, beams of light and everything. And here's our subject with a little sort of comb over and a background wall. So what we have here is basically a real-world representation of the same theoretical thing we saw earlier. So our correct exposure at 4 feet is f5.6. We double the distance, and there's now a quarter the amount of light, so the correct exposure here would be 2 stops less, f2.8, because 1 square now has to cover 4 squares. In our real-world application, that means that our subject, 1 meter from the light, correctly exposed at f5.6. Another meter away is our background wall, correctly exposed at f2.8. Okay, that's how that functions in the real world. So you take a picture, you'd be, if you were set for f5.6, your subject would be correctly exposed, your background wall will be 2 stops darker. Now why this matters and how you can use this is in playing around with these relative distances. Okay, and the relative distance between the subject and the light and the background and the subject and the background and the light. If we take another situation, so we have, here is our subject, here is our light, obviously we're familiar with them. Our subject is 1 meter from the light and is correctly exposed at f5.6. Our background wall is now 4 meters. This means there isn't just a quarter the amount of light, there's 1/16 the amount of light hitting it. That means this background wall is going to be very, very dark by comparison. Now that might be exactly what we want anyway for the photograph. You might want to have your subject against a totally black or almost pitch dark background. But what it can help you do is it can help you create the illusion of depth in what is effectively a two-dimensional object, a photograph, because of course we're only working in 2 dimensions when the real world is in 3 dimensions. Now how this can help is that you can add, say, another light if you want to. There's another light, look, isn't that amazing? That light can be used perhaps to outline the back of the subject, so it will make the edge of the subject bright in comparison to the background wall. You could add another light if you wanted. That light could shine onto the background. That light could create, say, a spot pool of light, or you could put coloured gel across that light to create a colour on the background that separates it out from the subject. Okay, don't forget the relative distances between the light, the subject, and other elements are what matter. They can allow you to create separation, as you have here with a large gap between these two. What you've got to remember though is that the distances are all important. Let's look at the actual overall distance graph. Now this bit we're familiar with. Okay, we have a distance here and we double it and we go from a correct exposure to 1/4 the exposure. Now as we extend the distance further away, we're only adding a meter at a time. Watch what happens to the amount of light falling. Okay, so this was our second scenario. Look, 1 meter, 4 meters, 1/16 the amount of light. The important thing to notice is that we're only moving a meter further away each time, but look at the relative difference in the drop-off of light. Now obviously the difference between one correct exposure and 1/4 that amount of light is really significant. You'd notice that difference. That's 2 whole stops, and it's the difference between 1 meter and 2 meters. The difference between 7 meters and 8 meters is still only a meter. That difference is between 1/28th of the correct amount of light and 1/32th the correct amount of light. Now that is pretty subtle. You would struggle to spot that with the naked eye. What that can mean in practical terms is it's very, very useful for things like large group shots, so that I can light, or anybody can light, a large group of people fairly evenly by making sure that they are all around this sort of end. Okay, I don't want some of them here and some of them here in relation to the light, because that means some of them will be sort of a bit darker and some of them will be absolutely pitch dark. So a shot like this of however many 100 and something people in a large dance hall, it is lit like this. I am up here with the camera on a balcony. I'm just on a balcony here like this. I have 2 big powerful flash heads. They are firing into the corners of a big white wall to create a big soft light. Here is the crowd of dancers. The light from these flashes obviously goes out like this, across, it comes out and it spreads across the dancers, but the distance across here is perhaps, well, let's estimate that. What's that? That's perhaps 15 meters across, shall we say? And I know from experience that I'm quite a long way back, so it's perhaps 15 meters across here. But these 2 lights have to cover an area that's probably more like 20 meters and 20 meters down here, and then probably, my maths is appalling, I apologize, probably more like 25 to 30 meters. So which means the differences between these people is much more like the differences between somebody at 7 meters and 8 meters from a light, so very, very subtle and hard to notice. By comparison, if you can imagine, if instead, rather than having my lights way sort of out of this shot, way up here, in the balcony, far, far away from them, instead, if I lit with the lights just here and just here, well, these people might be correctly exposed or might be very bright. By here, they'd be getting quite dark, and by here, they'd be pitch dark. Okay, if I had instead, instead if this light was just there, and this light was just there, this would be lit, this would get dark very, very quickly, this would be lit, and this would get dark very, very quickly, because of the natural fall off of light, because I would have people much more in this region of dramatic, significant fall off from meter to meter, rather than down here. Now, as I keep stressing with these sort of things, this is a basic law of physics. You can't cheat it, but if you're ever faced with situations like this, you know how to get round it. Increase the light to subject distance so that if your subject is of any sort of decent size, it's going to fall across this sort of area in terms of difference of light, rather than this sort of area in terms of difference in the amount of light, because this is a huge difference and this is only a very, very small difference. I just want to go over this one more time because it's such a fundamental principle, and if I'm honest, It's something I struggled with a lot when I started. Let's look at the same thing, but on a much smaller scale. We're not talking about a group shot of several hundred people. We're talking about two very small objects, but we're still talking about this relative distance, okay? But the numbers might be slightly different. And what we have here, two little espresso cups. Obviously, you can tell from the shadows and the highlights, the light is coming from over this side. We've got a fairly bright area here, right down to very, very dark shadows here. You can probably guess, if by now you're starting to take this on board, that what it means is that this was shot with the light and the subject pretty close together. Here is how this was shot. There we are, camera, mugs, and that is how close the light is. Now, of course, that is, what, that's perhaps not even 30 centimeters. And it means that on a scale as small as that, the difference between even this mug on the left and this mug on the right is enough for it to be sort of not exactly in this territory, but of course there's enough of a difference here for you to notice. Look inside the rim of the cups. So here we've got, it's a mid-white that goes down to slightly darker here. We're only centimeters further away, and exactly the same cup has gone noticeably darker. Okay, noticeably darker with a distance of a few centimeters further from the light, because the light is this close to them. Okay, so of course the relative differences are much more noticeable when you're closer to the light. Let's change this around. Here is a much more even one. Look, that's much more of a mid-tone. That's much more of a mid-tone. This shadow here looks remarkably close in tone to this shadow here. Now you can probably guess what's coming. All I did was move the light much further back. Now, of course, in both cases, I've adjusted the exposure so that it's correct for this, because what you mustn't forget, no matter what scale you're using, is that the amount of light will fall off, so you may need to adjust your exposure so that you get the correct exposure for what you want. But the relative difference in distance from subject to light between these two cups is now considerably smaller, because, of course, the overall distance is now, what, a meter and a bit at least from the light to the subjects. So when it's much, much closer, you can see a dramatic difference between the bright blown out areas here and the pitch dark shadows down here. And then when it's further away, they're much more evenly lit. So what we're seeing here is basically a smaller scale demonstration of exactly the same principles as we saw with the massive group shot, because you can't escape this, I'm afraid.
There you go. As I've said a couple of times, I found inverse square law very difficult to get my head around to begin with. So I hope I've managed to explain it clearly. If not, please stick any questions you've got in the comments below. Otherwise, subscribe, hit like if you like it, all that sort of thing, and I'll see you next week.